and welcome to lecture 14 of analog integrated circuit design. In the previous lecture, we tried to make a better op amp and we were midway through the analysis to see whether it is really better or not. And the topology of the op amp that we came up with was like this. The first transconductor converts the input voltage to a current, and that is passed through a current controlled voltage source made using a second op amp, which is simply this GM2 and CL, and the current to voltage conversion happens because of this C that is connected from the input to the output of this op amp. This is basically a current controlled voltage source of a transimpedance 1 over SC. We derived the transfer function of this op amp and we saw that the transfer function has 1 0 and 2 poles, and we were trying to make intuitive sense of the pole values that we obtain. And to do that, what we also did was we removed this C and evaluated the pole values, which turns out is very easy to do, GO1 by C1 and GO2 by CL. Okay. Now, when we do have the C, we will get these pole values, this complicated thing here and that complicated thing there. And this first one we made intuitive sense out of by seeing that it is GO1 divided by some other capacitance. Initially we had GO1 by C1, now we have GO1 by C1 plus Miller multiplied C. Okay. And we also saw why Miller multiplication happens. Similarly, now for the second pole it is GO2 by CL. First of all, even the numerator has changed, it is GO2 plus some other terms which represent conductances, and in the denominator we have CL plus all of this stuff. So, does this make sense? Indeed it does, as we will see shortly. So, again let me repeat the op amp that we have: GM1, GO1, C1, GM2, GO2 and CL, and we have C from there to there. Okay. So, now originally the conductance here was GO2, now it appears to be something different. Originally the capacitance here was CL, now it again appears to be something different. Okay. So, again what we can do is to examine the network around this, and you also know that poles are characteristic of the circuit, they have nothing to do with where the input is applied. So, we can examine the circuit with a 0 input and determine the poles. Okay. So, when we have 0 input, this transconductor GM1 is as good as not being there. So, the circuit we have is something like that. Okay. I will draw only the capacitors C, C1 and CL, and I do this and I also try and see what is the capacitance associated with this node, that is from this node to ground, and I do this because this is where GO2 was, right, this is where GO2 is. Originally we had only GO2 and CL from this node to ground. Now we have some conductance and some more complicated network of capacitances, but it is not all that complicated. All we have is this CL in parallel with the series combination of C and C1. So, what does that give you? The total capacitance will simply be CL plus C, C1 by C plus C1. Okay. And if we go back to the expression, you see that the denominator is exactly that, it is simply the load capacitance plus the series combination of C and C1, that is all. Okay. Similarly, now the conductance, the term in the numerator seem to contain some GM2, okay, whereas GM2 is a transconductance. How did this happen? I think all of you are aware that you can take a transconductance GM2 or a voltage controlled current source and make it appear like a conductance using feedback. Okay. What does the transconductance do? If I have some voltage here, it draws a current GM2 times V. Now, if I connect an input and the outputs together, what does it mean? If I have a voltage here, it draws the same current from that voltage, and what is that? That is nothing but a resistor or a conductance. Okay. If you have a voltage and you draw there is an element which draws a current that is proportional to that voltage, that is nothing but a conductance, and the conductance of this is GM2, or the resistance is 1 over GM2. Okay. So, something like this must be happening, that is the transconductor is in feedback, and that is why we are ending up with a conductance which has a term containing the transconductance GM2, and clearly there is indeed feedback here. You see that there is feedback with C and C1 around GM2. Okay. Now, I will draw only that part of the network. Okay. If I apply a voltage V, the voltage here will be V times C by C plus C1. Okay. It is simply a capacitive division of the voltage V, and the current drawn here will be that voltage times GM2. So, that is nothing but C by C plus C1 times GM2 times V. So, clearly this entire network, as far as the contribution of the transconductance is concerned, looks like a conductance of that value. Okay. So, the transconductance, because it is in feedback, contributes a conductance of C by C plus C1 times GM2. In this case it is about GM2 because all of this V was fed back to the input. Here only a fraction of V is fed back to the input. So, it is smaller than GM2, but nonetheless related to GM2. Okay. So, that is the conductance contributed by GM2. In addition to this, you have GO2 itself over there. So, we expect that we will have C by C plus C1 times GM2 plus GO2, and indeed if you look at the expression, we have GO2 plus the effect of GM2 being in feedback. Okay. Now, we also have this extra term, because what we have here is not only C1, we have GO1 in parallel. Okay. So, that gives you some extra terms, because if we did not have GO1 at all, you would have only this capacitive network. We also have GO1 here, and that gives you some conductive portion which is related to GO1. Okay. But typically you expect that GM2 is much more than GO1 and GO2. So, in fact, the dominant conductance is expected to be this middle term here, okay, this one alone, and the other two will be smaller. Okay. So, although again whereas the expression looks complicated, it is very easy to make intuitive sense out of it. It is again some conductance by some capacitance. The conductance happens to come from the output conductance of the second stage as well as the transconductance being in feedback. Similarly, the capacitance comes from the load connected to the second stage, which is CL, plus the series combination of C and C1, because that is how they are connected in the circuit. Okay. Also, another thing we observed was that this P1, which was minus GO1 by C1 without C, moved to a lower frequency because the apparent capacitance increased. Now, what happens to P2? It is GO2 by CL, and here we see that both numerator and denominator have changed. The numerator has increased, the denominator also has increased, but it is important to keep in mind that GM2 is expected to be much more than GO2. Okay. In fact, that is how you get gain. The gain of the second stage is GM2 by GO2, and you expect the DC gain to be at least 10, if not in the many tens or hundreds. Okay. Whereas the capacitance has become CL plus some value, which you generally expect it to be of the same order of CL, same order as CL, or even smaller. Okay. So, the denominator increases, but only modestly, the numerator increases enormously. So, it turns out that this P2 moves to a high frequency compared to the case where we did not have a C. We considered the case without C only because the poles were easy to calculate, and also it turns out that it is a common scenario. You have one amplifier after another, and if you cascade a number of amplifiers, you get a number of poles from each amplifier's output. Okay. Now, in our case we have two amplifiers one after another, and our op amp looks like such a structure with two amplifiers and a capacitor connected from the input to output of the second stage. And when you do that, it turns out that one pole moves to the lower frequency and another pole moves to a higher frequency. So, such a thing is known as pole splitting. Okay. So, it turns out that it is in fact a useful thing to have when we are trying to make op amps, because after all what would we want? We wanted the op amp to behave like an integrator, that is a single pole system. And we also saw from stability criteria that if you have extra poles at all, they should be at much higher frequencies. Now, here in this case what happens is one of the poles moves to higher and higher frequencies, and that is a good thing for an op amp, as we will see also in future analysis. Okay. So, in summary, the new op amp that we came up with has 2 poles and a 0, and the poles are given by these expressions. Okay. And the 0 we already determined, it is at plus GM2 divided by C. Okay. So, this because it has 2 transconductance stages one after another, it is known as two-stage op amp, and our earlier op amp which has a single transconductance stage loaded by a capacitor this is known as a single stage op amp. And in each of these cases we could use voltage buffers after these op amps, but like I mentioned earlier, voltage buffers are harder to make in these CMOS technologies, especially with low voltages, low supply voltages. So, we typically tend to use these op amps without explicit buffers. These things will become clearer when we come to circuit realization of these op amps. And this has 2 poles. I will write only the approximate values here. It also has a 0 which is at plus GM2 by C, whereas the single stage op amp, if you recall, it has a single pole at minus GO1 divided by C. Okay. Now, what is the unity gain frequency of the single stage op amp? That is nothing but GM1 divided by C. And what is the unity gain frequency of the 2-stage op amp? It is also GM1 by C, because after all recall how we came up with this topology. We have this transconductance GM1 whose output current is passed through this capacitor, okay, by putting the capacitor in feedback around a second op amp, so that we form a current controlled voltage source. So, the approximate transfer function from the input to the output is still GM1 by SC times VE. So, that means that the unity gain frequency here is GM1 by C as well. Okay. Now, this can also be verified very easily. If we draw the magnitude response of the 2-stage op amp, it will have a DC gain of GM1 GM2 by GO1 GO2, which is the product of the DC gain of the 2 stages, and there is a pole and at that point there will be a break point and the gain drops at 20 dB per decade. Okay. And then at some frequency there will be a second pole P2, and then some other frequency there will be a there will be the 0 Z1. Okay. I have assumed that P2 is smaller than Z1, which may or may not be the case. Now, here you see that the behavior is first order all the way down to P2, and this is the 0 dB line. I am assuming that the behavior is first order all the way down to the 0 dB line. This we anyway know has to be true for good stability. Okay. From our earlier study of Bode plots and Nyquist criteria, we have seen that the system has to maintain, the loop gain has to maintain first order dependence on frequency all the way down to unity loop gain frequency. Now, if we place this op amp, our 2 stage op amp in unity feedback, the unity loop gain frequency of this feedback loop is nothing but the unity gain frequency of the op amp itself. So, we will assume that we have made a unity feedback configuration like this. So, in this case the unity loop gain frequency will be the unity gain frequency of the op amp, and first order behavior has to be maintained all the way down there, and because this is first order behavior, this frequency is easily seen to be the product of this DC gain and this pole. Okay. Times the magnitude of P1, and if we evaluate that, P1 is nothing but G01 by okay. So, that cancels with that, and this approximately cancels with that, and this C times Gm2 by Go2 plus 1 is much larger than C1. So, this C1 can be neglected, okay. And then this Gm2 by Go2 term cancels Gm2 by Go2 plus 1, because Gm2 by Go2 is a number that is much more than 1. So, the unity gain frequency approximately is Gm1 by C. Okay. Now, remember this is the unity gain frequency that we were trying to implement. So, it is not surprising at all that we get the same number, but just wanted to show that when you calculate it without knowing anything about the circuit, you simply calculate it as a product of the DC gain and the first pole, assuming that first order behavior is maintained all the way down to 0 dB gain, you will get the same answer. Okay. And it is nothing but the unity gain frequency of the single stage op amp we started off with. Okay. After all, we made this as an improvement to that one without changing the unity gain frequency. Okay. Was this fine? Now, so what is the advantage of this after all? The advantage of the 2 stage op amp is that the single stage op amp has a DC gain which is Gm1 by Go1, whereas the 2 stage op amp has a DC gain which is Gm1 by Go1 times Gm2 by Go2. Okay. So, the DC gain of this can be significantly larger than the DC gain of that one. Both have the same unity gain frequency, and this has a single pole, whereas this has multiple poles and zeros. So, while stability is unconditional with a single stage op amp, we have to worry about the stability of the 2 stage op amp because it has multiple poles and zeros. And as I have mentioned earlier, stability for us not only means not oscillating, it is not just that, it also has to be well behaved. We should not have ringing and so on in the step response. Okay. We will see the conditions for that soon, but the advantage is very clear. We get the DC gain of the single stage here, whereas we get DC gain of 2 stages, and we have designed it so that the unity gain frequencies are the same. So, we have to compare the other things. Okay. Now, besides this, there is also another advantage of using a 2 stage op amp compared to a single stage op amp. Let me copy these things over. And that has to do with what happens when the load is resistive. Okay. That is, let us say we have an external load which we also connect to this and connect to that one. Okay. And in general, when you do that, it is expected that the load conductance GL is much more than GO1. Okay. That is, RL is much smaller than RO1. Similarly, here GL can be much more than GO2. Okay. So, the DC gain in this case will be GM1 by GO1 times GM2 by GO2 plus GL. Similarly, here the DC gain will be GM1 by GO1 plus GL, and GL will dominate GO1, GL will dominate GO2 there. Okay. Now, clearly you can see the problem here. In case of a single stage op amp, if you do have a resistive load, you have to make this GM1 much more than the load conductance, so that you get a significantly less DC gain. Okay. The DC gain required may be of the order of thousands or even higher, and when you try to implement a large value of GM, you end up dissipating a lot of power, and that is a serious problem for circuit design. Here what can be done is, GM2 does not have to be much more than GL. It has to be more than GL, but not by a factor of 100 or 1000, but it could be more by only a factor of 10, let us say. That is okay, because you can still keep GM1 by GO1 very large and get a DC gain that has a large respectable value. Okay. In other words, you place the burden of getting a large DC gain on the first stage. The first stage is isolated from the load, so it will not be affected by how low this value of RL is, and the second stage has to provide only a modest gain. So, when you have resistive loads, this is really only the feasible alternative, because if you try to use this, it is possible, but you will have to end up using such a large GM that it will be very wasteful of power. Okay. Now, what about stability with the two stage op amp? I said that you have multiple poles and zeros, so you have to worry about stability. So, we have the transfer function of the op amp to be A naught, which is the DC gain. I will write it in this form, 1 minus S by Z1 . Okay. Let me do it like this, so that minus P1 and minus P2 are positive numbers. Okay. Now, what about stability? Stability margins and so on are determined by loop gain, and the loop gain itself depends on the feedback loop that you place the op amp in. Okay. So, let us say I realize an amplifier of gain k, okay. The loop gain of this, let us say the transfer function of the op amp itself is some A of S. A of S is VO by VE. The loop gain is what I get by breaking the loop and going around it and seeing what comes back there. So, that will be nothing but A of S divided by k. Okay. This we have seen earlier. So, this is the loop gain. Now, so the loop gain depends on the value of k, which means that it depends on the amplifier that we are trying to implement. Okay. Now, let us say we take the op amp, and the gain of the op amp, A of S of the op amp has this magnitude. Okay. So, this is modulus A, that is modulus V naught by V E, and it has a pole at P1 and it has a pole at P2 and as 0 at Z1. Okay. This is the gain or the transfer function of the op amp. Now, what will be the loop gain? Depending on the value of k, this curve will be shifted down by 20 log k on the Bode plot. Okay. So, if k equals 1, this itself is the loop gain. If k equals 2, it will be like that. Okay. And similarly, if k equals 4, it will be like that and so on. Okay. So, this will be the magnitude of L for k equals 2, the magnitude of L for k equals 4 and so on. Also, if I plot the phase response, what happens? There is a 45-degree phase shift at the first pole, and then the phase reaches minus 90. At the second pole, there is another 45-degree shift, and at the 0, there is another 45-degree shift, because this is right half plane 0. Okay. So, we will not worry about the details of the phase right now, but the point I want to make is that we have seen that the stability margin depends on what happens at the unity loop gain frequency. Okay. For the 3 cases I have considered, k equals 1, k equals 2 and k equals 4, these are the unity loop gain frequencies. And you can see that the phase keeps going down monotonically for a function like this. So, we are interested in the phase margin, that is how far the phase lag is away from a minus 180 degrees phase lag. Okay. So, clearly it gets worse for lower values of k. Okay. This is the worst, it has the maximum phase lag. This is better, it has less phase lag. This is even better, it has the least phase lag. Okay. So, we have the highest phase lag for k equals 1. Okay. Now, this is relevant because normally when you design an op amp without any further information, you simply have to assume some value of k. Obviously, the value of k that you have to assume is the worst case, which is in this case 1. That is, you assume that whoever is going to use your op amp can use it with various values of k, and you design it for the worst case, and the worst case happens to be 1. So, if k is 1, the loop gain is nothing but the op amp's gain itself. So, it is easy, in a way you can design the whole thing without worrying about which feedback loop there is. You evaluate the gain of the op amp and assume that that itself is the loop gain and adjust it for stability. Okay. Now, this is not a general procedure. When you do know what value of k you have to design it for, you design it for that particular value. Okay. You do not design it for the worst case value. It is only when you do not know that you design it for the worst case value. We will assume for the purpose of this lecture that we will design it for k equals 1. Okay. So, if we have k equals 1, the loop gain equals the gain of the op amp, or the unity loop gain frequency equals the unity gain frequency of the op amp. Okay. Now, let us again examine the function that we have, the magnitude and phase. A of s is A naught times 1 minus s by that 1 plus s by minus p 1 plus s by minus p 2. Okay. So, as I plotted earlier, you start with A naught and then you have a 20 dB per decade slope in the magnitude plot. We have to make sure that these other poles appear beyond the unity loop gain frequency. Okay. This we have seen during our discussions of stability analysis, and also these zeros have to appear beyond the unity loop gain frequency. Okay. So, this is the condition that we must satisfy, and it should be beyond by a certain value, And how do we determine that value? For that this is the magnitude of A, we plot the angle of A, which is also the angle of loop gain in this case. So, in our case we have a right half plane 0. Okay. Now, the right half plane 0 introduces phase lag. Okay. If you write the expression for the phase of this, the angle of A of j omega will be minus tan inverse omega by z1 minus tan inverse omega by p1 minus tan inverse omega by minus p2. Okay. Here P1 and P2 were the poles which were negative numbers. So, this is how I have written it. So, each of these contributes to phase lag, and the total phase lag happens to be minus 270 degrees. Now, what is it that we want? At the unity loop gain frequency, which for k equals 1 is the unity gain frequency of the op amp itself, we should make sure that this margin, which is the margin between minus 180 degrees and the actual phase at the unity loop gain frequency, is sufficiently high, that is called the phase margin. Okay. And again, in absence of any specific information, we will assume that the phase margin has to be, let us say 60 degrees or so. Okay. So, this again is not a sacred number, you could have phase margin anywhere from 30 degrees to 80 degrees or whatever you want based on the context, but generally we assume that 60 degrees is a good number and use that. Okay. Now, what does this mean? The total phase margin is the total phase lag, which is minus tan inverse omega by z1 minus tan inverse omega by p1 minus tan inverse omega by minus p2, okay, plus 180 degrees. It is the distance from 180 degrees. So, first of all, what omega are we talking about here? This is the omega u loop, unity loop gain frequency. That is where the phase margin is measured, and the unity loop gain frequency is minus tan inverse gm1 by c, and the 0 z1 is at gm2 by c. Okay. So, this is the first term, and it simply reduces to gm1 by gm2. Okay. The second one, this is the ratio of omega u loop divided by p1 and the tan inverse of that. Omega u loop is here and p1 is there, and they are very widely separated. What is the factor of separation between these two? It is very easy to see. This is 20 dB per decade drop. So, this is nothing but the separation between these two is the same as this number A naught. Okay. The ratio of these two numbers, omega u OPA by P1 is A naught. This is something we know already. Okay. Omega u OPA can be approximately calculated as A naught P1 when the roll off is predominantly of first order. Okay. Now, because of that, this is tan inverse of a large number. So, this is simply minus 90 degrees. Okay. That can also be seen from the plot. The phase drops down to minus 90 and stays that way for stays that way. Okay. This is the phase lag due to P1. Now, because P1 is far from omega u OPA, it would have reached 90 degrees somewhere here, and then it stays at 90 degrees all the way there, the contribution due to P1. Okay. And finally, we have minus tan inverse omega u loop by P2. This is something that has to be calculated. I will just leave it as it is, omega u loop by P2 plus 180 degrees. Okay. And this is nothing but 90 degrees minus tan inverse gm1 by gm2 minus tan inverse omega u loop by P 2. Okay. Let me write it as minus the sum of these two. This is the phase lag due to the right half plane 0, this is the phase lag due to the second pole, okay, and we would like this to be let us say 60 degrees. So, what does this mean? The sum of these two should be 30 degrees. Now, it is up to us to apportion the 30 degrees between these two. We can have a large phase lag due to the 0 or the pole, but the sum of them has to be 30 degrees. Now, if you make one of them very large, the other one has to be made very small, and that is usually very difficult. Okay. And also you see that the phase lag due to the 0 depends only on the ratio GM1 by GM2. Clearly, to make this small, you have to make GM2 much more than GM1. This is very clear, right? That guideline appears directly from this. GM2 has to be more than GM1 by a significant factor, because if GM2 were equal to GM1, this would be 45 degrees, and there is no way to make this 30 degrees. Okay. In fact, we have to keep this number well below 30 degrees, right. So, let us say for instance, we will take GM2 equals 4 times GM1, then this particular number will be tan inverse 1 by 4, which is approximately 14 degrees. Okay. So, this sounds like a reasonable choice. Then we have 14 degrees from this, and we can have 16 degrees from there. We will have 16 degrees for this one, and we have to adjust the value of P 2, so that this number happens to be 16 degrees. This in essence is the design of the op amp at this level. Okay. We have not yet gone to the transistor level. There is a reason we discuss the op amp at the level of the control sources before going on to transistor level, so that these issues with transfer function and loop gain and so on come out very clearly without being distracted by the transistor level details. Okay. So, what do we do when we have to design a 2-stage op amp? We have to choose the second stage transconductance, so GM much more than the first stage GM. Let us say we make it 4 times, again not a sacred number, you could choose 3, you could choose 6, whatever is convenient. If we do choose 4, the 0 will give a 14 degree phase lag, and you will have 16 degree phase lag left for the second pole, and you can adjust the second pole, so that you get only 16 degrees phase lag from that. Okay. Now, what does this give you? First of all, omega u loop itself is GM1 by C, and P 2 is GM2 C by C plus C1 divided by CL plus CC1 by C plus C1. Okay. And this is the ratio omega u loop by P 2, and that is tan 16 degrees. Okay. I have here neglected the contribution due to GO2, okay, because that is expected to be much smaller than the contribution due to GM2, right. Now, I will expand this out, I will get okay. Equals tan 16 degrees. Now, what comes out of this is a quadratic equation in C. Okay. So, given CL and C1 and the values of GM1 and GM2, you can solve for this. Okay. So, let us try to put it in a more illuminating form. We will have GM1 by GM2 times one over C square appears there, and Okay. And this 16 degrees came because we chose GM2 by GM1 of 4, otherwise we would get some other number. Okay. Now, I will divide both sides by CL square. It makes sense to express everything as a fraction of the load. Okay. So, here I will get C by CL, and here I will get C1 by CL, and here I get C by CL times C1 by CL. Okay. So, that is what this whole thing is. So, this is a quadratic equation in C by CL square, and it intuitively makes sense to normalize everything to CL, because if you have a large CL, then that means that the unity gain frequency of the second op amp that we use to make the current controlled voltage source tends to be small. Okay. And we already said that the unity gain frequency of the overall op amp has to be smaller than that unity loop gain frequency of the second loop, otherwise the second loop is not behaving like an ideal feedback loop. So, that means that we will have to have a large C or a small omega u. Okay. So, if you have a large load capacitance, all the other capacitance also tends to be larger. Okay. So, you can calculate C by CL from this expression based on the ratio GM1 by GM2, the phase margin that we have. I will put phi m prime because this is the phase lag, excluding the phase lag due to the 0, and it also depends on this ratio C1 by CL. Okay. So, the bottom line is it can be calculated based on these things, and then you can verify it with simulation whether it is exactly right or not. Okay. Now, let us go back here. We have the expression for the poles and the 0. Now, in certain conditions, the expression for this pole can be further simplified. Okay, this P2. Now, what is the expression for P2? It is minus GO2 plus GM2 C by C plus C1 divided by CL plus C C1 by C plus C1. Okay. Now, let us imagine a case where C is much more than C1. Let us say the design values turn out to be like that. Okay. So, what does it mean? I will approximate C plus C1 by C itself. So, P2 becomes minus GO2 plus GM2 divided by CL plus by CL, sorry, minus GO2 plus GM2 divided by CL. Okay. Now, does this make intuitive sense? Again, let us go back to the structure that we have. Okay. Now, what we are assuming is that this C, the capacitor C here is much more than the capacitor C1 over there. Okay. So, what does it mean? Earlier we assumed that in this feedback we had a division ratio of C by C plus C1. Now, if C is much more than C1, there is no division at all, any voltage that appears here also appears there. Okay. So, C is approximately like a short circuit, right. In that case, we will have this topology when this is a short circuit. I will just short this. Now, if this GM2 is shorted on itself, okay, the conductance is nothing but GM2 itself. Okay. So, if we have GM2 like that, it looks like a conductance whose value is GM2 or a resistance of 1 over GM2. So, the total conductance is GM2 plus GO2, that is what we see here, and there is a mistake in the denominator here, it should be CL plus C1. Okay. Clearly, you see that if C is very large, what happens is you will simply end up with C1 here. Okay. And we have these two capacitors C1 and CL in parallel. So, we have GO2 and GM2 in parallel with CL and C1, and the second pole expression becomes even simpler than before. It is simply GM2 plus GO2 divided by C1 plus CL. Okay. Now, this is true only when C is much more than C1, which may or may not be true always. Okay. But what you can do is use this expression for P2 as a first cut approximation. Okay. Now, that is useful because we earlier said tan inverse omega u loop divided by P2 should be 16 degrees or some particular value that we wish to have. Okay. Now, omega u loop is GM1 by C and P2 is GM2 plus GO2 divided by C1 plus CL. Okay. So, now you see that we have linear equation in C, it is much easier to solve. So, what you can do is you can use this further approximation for the value of P2 and get a first cut value of C based on the linear equation solution, which is very easy to compute. Sometimes when you are calculating things in your head, this may be the method to follow. And finally, you can see really whether C is much more than C1 or not. Now, if C turns out to be much more than C1, you do not have to do anything further. If C is not much more than C1, what you will have to do is to go back and recalculate based on the quadratic equation. Okay. Thank you. I will see you in the next class.